Hello, this is SND College of Engineering and Research Center, Yeola, lecture series for first year engineering department, Engineering Physics. I, Dr. Chaudhary Vivek Sitaram from first year engineering department. Today's welcome. As we know, Schrodinger's equation. The Schrodinger's equation plays the role of Newton's law and conservation of energy in classical mechanics. That is, it predicts the future behavior of a dynamic system. It is a wave equation in terms of wave function, which predicts analytically and precisely the probability of events or outcomes. The detailed outcome is not strictly determined, but the given a large number of events, the Schrodinger equation will predict the distribution of results. So classically 1 half mv square plus 1 half kx square is equal to E, and quantum mechanically conservation of energy Schrodinger's equation. Here we know HSI is equal to E psi. The energy becomes the Hamiltonian operator. So the kinetic and potential energies are transformed into Hamiltonian, which acts upon the wave function to generate the evolution of the wave function in time and space. The Schrodinger equation gives the quantized energies of the system and gives the form of wave function so that other properties may be calculated. Now here in today's lecture we will see the energy levels of a particle enclosed in a one-dimensional potential box of infinite height. So the height of the box is infinite. So particle is unable to overcome that much height. So whatever may be the energy of the particle is inside the well or inside the box. Consider a particle of mass m moving in a one-dimensional box of infinite height. So V is equal to 0 inside the box and infinity potential at the two wells. So V is equal to infinite less than the 0 and greater than the L. So the one-dimensional time independent Schrodinger's wave equation for the particle is d by 2 psi by d by x square plus twice m upon h cross square into E minus V of psi is equal to 0. So here the potential energy V is equal to 0 between the walls. Hence the equation reduces to d2 psi by dx square plus twice m upon h cross square into E of psi. So what it gives? So minus h cross square upon twice m d2 psi by dx square is equal to E of psi. So one dimensional square well potential. So particle is present inside the well, but it is unable to overcome this much height of, because it is having the infinite height. That's why particle cannot be present outside the wall. The general solution of the above equation is equal to psi is equal to a sin kx plus b cos kx, where k is equal to under root twice a me upon h cross, and where a or b are the constants. So from that the particle cannot penetrate the wall, as psi is equal to 0 at x is equal to 0 and psi is equal to 0 at x is equal to L. So by applying all these boundary conditions, d psi by dx is equal to a k cos kx minus b k sin kx. So d2 psi by dx square is equal to minus a k square sin kx minus b k square cos kx, which is equal to minus k square of psi x. So as we know this, by putting this, so h cross square k square upon twice m psi is equal to E psi. Now to be valid wave function, psi must satisfy the above boundary conditions. That is, psi is equal to 0 for x is less than 0. The wave function is not present outside the well. So that's why particle is not present outside that well, because it is having infinite height. That's why psi, the last equation becomes, after applying these conditions, psi is equal to a sin kx plus b cos kx. So from this, again if we apply boundary conditions, so b will be 0 and psi is equal to a sin kx. So for generalize, the over the other wall, if we put psi is L is equal to 0 for psi L, that is at x is equal to L, then the psi L is equal to a sin kl, and where is equal to 0. So in this condition a will not be 0, so sin kl, so kl will be is equal to n pi, because 0 is not possible. Now if we observe the particle in a box, so for n is equal to 1, it is having one distribution. For n is equal to 2, the wave function is distributed like this, and for n is equal to 3, the wave function is distributed like this. But if we observe the probability of finding the particle into that well, now the wave functions become psi is equal to a sin n pi x upon L, and k is equal to like this. So from this, if we observe this, then the probability of finding the particle into that well, and for different values of n, so p is equal to n pi upon nh upon twice L, where n is equal to 1, 2, 3. So and 1 of mv square is equal to En. So in the last equation, E is equal to n1 square plus n2 square plus n3 square hs square upon 8 ml square. Thank you very much.